Hello to all of you today. I'll be talking about time series in general, obviously through the lens of us as QuestDB. My name is Adam Cimarosti. I am one of the core engineers on the product. And just as a bit of background, what we tend to focus on is performance. Performance tends to be a key thing in time series data. And QuestDB itself started in 2014, sort of as a side project out of a need, and grew over time. Eventually, a company was formed in 2019, and the product is all open source. We have some variants of the product which add a few bells and whistles, which you can use. But yeah, it's Apache 2.0. Myself, I'm a software engineer. My background is in financial services. I've worked on trading systems and things like that. But actually, for most of my career, I've been working on data platforms, things like pandas before pandas existed, other databases and things like that. And I've joined QuestDB about 2 years ago. And yeah, so what I'm going to talk about is what is time series, because this is maybe not always obvious. And from there, really talking about the architectural differences between that and a more regular database, and talking about how the type of questions that you ask a time series database is different, and how you can view time series in a different way depending on whether it's more recent data or not. And then how this all plays together with other things which are not time series. And the role of open standards in that, and what we're building to make all this possible. So to answer what is time series, yeah, so this is QuestDB in the background powering Grafana. And one of the data types that we support is actually geolocation. This is data that you see played back in real time, but 8 years passed because we're not a taxi company. But these are really the type of things that you see time series shine. So if you want to track a large amount of things, then you kind of can see their position, and in this case, where customers are being dropped off, or things like that. Now, all these things are actually just SQL queries running in the background. And for a use case like this, you can see them ticking quite quickly. And the way that this stuff works is that it's just a query at the end of the day. So if you take that query and you grab it and you put it into our web UI, which gives you an idea, and run it. Sorry, this is pre-recorded. I'm talking faster than then. So this returns that query over 1.6 billion rows in like 8 milliseconds, which is really where all the stuff that I was showing earlier on how you can optimize the storage for query performance really starts to shine. And this is a non-trivial table. It's got quite a few fields, but then I'm only really asking for, what is it, like 3 or 4 fields out of here. So because of that, like 3/4 of all those fields never even get access because it's all columnar. And yeah, this is 1.6 billion rows. For context, this is about 10 years of data, ticking on average 5 events per second. Compressed is about 24 gigabytes of data. Uncompressed is quite a lot more, and we have customers doing this sort of stuff on relatively commodity hardware for, with terabytes of data. And so the type of fields that you might have for something like this is like the vehicle ID, the GPS position, where is it, the booking ID, how many people are traveling and how far you've traveled, and a timestamp. And it's not only taxis, of course. Everybody needs, but a lot of use cases need time series. In the trading world, you may want to record market data or trades, and you're going to have your order IDs, your price quantity, and stuff like that, and a timestamp. If you have energy, then depending on what it is that you're doing, you have things changing and all sorts of fields that you need to capture, and a timestamp. And we have customers with even more unusual use cases, such as they want to run a rocket engine test. They plug a whole bunch of sensors around the test that they're doing, and they capture the fields for that and a timestamp. So stuff happens. A time series database records it. And the key differentiator here is that this can be often millions of rows per second on a single instance. And as such, our database and time series database in general as a workflow tend to optimize for that. So this means that all the pipeline and infrastructure is optimized for capturing events on the go, nonstop, whilst being able to handle queries, and really prioritizing writes over, say, deleting or updating data. This really is the key architectural difference between them. So the way that we do this is that we do this via columnar storage. We also partition things, so by day or things like that, or by year, by time period in essence. And you may have your timestamp, that's columnar, so we can access it when we need to. Your price and the symbol of what it is, in this case, it's a trading example of what it is that you're trading, and the final quantity that you're capturing. And like any modern fast database, these are all values that are held natively. So these would be like int64s or float 32s or whatever it is that it needs to be. But the key thing, if you look at the first column, here's this, summarized as timestamp 0, 1 to 3 to all the way to 6. These are ordered, and this allows us to do very fast index-less time series queries, as I'm going to demonstrate later, with another key feature, which is often typical of time series databases, is that often you tend to have identifiers that come in quite commonly. So a ticker symbol like, I don't know, AMD, you would see that repeated multiple times, but you don't know in advance how many of these are going to be. So we have support for that, and I think pretty much all time series databases tend to do that. And native data types I talked about. And this structure is actually not that cheap to maintain. So I'm going to peer into how this works. And the way that we get this working within our own database is through a write-ahead log. And we sort of separate out the act of getting the data written into the database as quick as possible from the maintenance of this format. No, it's fine. We've moved far enough. I can play the video later. It's not a problem. So you can imagine that you would have, say, 3 client connections into the database, and what the write-ahead log allows us to do is have the clients connected to the database, and then all of them independently have their state handled individually for them. So we dedicate a writer per connection, and these can all independently write their own data. And we then only summarize the the order of events that have happened into another component, which we call sequencer. And as a transaction comes in, then we also log where that transaction happened. So if you think about a transaction, this could be thousands of rows coming in. That's quite a bit of data. In parallel, another connection can come in, but we've only really wasted 28 bytes to say the order of where that transaction was. So we really managed to parallelize as much as possible here. And transaction can come in. You never know where they're going to come in next. Maybe on the same connection. That gets logged, or another connection on would receive the transaction after that, which gets logged, and so on and so forth. Now, this is sort of the cheap part. We managed to then store all the data, and if we then peer into one of the transactions, then it's mostly in order. But if we look at another transaction, then together the timestamps don't really align. So separately, we go through and take the first set of timestamps, merge them in with a second set of timestamps, which we would have on disk, and then the last set of timestamp. And we have this job that sort of runs in the background continuously, updating the queryable data set. And this is all, this sort of it's an n-way merge of the data that's coming in. And yeah, this sort of happens all the time, and it happens as quickly as possible. So if there's spare capacity on the machine, it'll just catch up as soon as possible. So you'll see your results showing up pretty much in milliseconds. And so it sort of solves the problem of fast data ingestion together with having a layout for the data that's as fast as possible for time series-based queries. So this is really the other differentiator between a time series database and a regular database, is that the type of questions that you tend to ask are different. And so I'm going to give you a few examples. These are relatively straightforward ones. But if I wanted to know how many events I've captured in a table for a weather data, these queries, by the way, they're all things that are available on a demo.QuestDB.io, and they're there. So that's where I've pulled these things out. So this took the sample by and did effectively a time-based group by, which is a bit of a. You can do all these things with a regular database, but this is one line here, and it's like that much more otherwise on a more general database. And this is all columnar and already ordered by timestamp. This is all quite fast. Another time-based query would be to figure out, if I go back here, the last row, for example, has 33 events. I want to know what's in there. I just want to look at the first, say, 3 hours of that year. And I can then ask for the fields that I want. It'll only pull out those. And then I can say, for that timestamp is within that range. And I will get the answers back. And you see that it's only in those hours that I asked for. And then there's other time-based group bys. So I want to do a group by of, in this case, no longer weather data, but trading data. And I want to do a group by the symbol and side, but I want to know what the latest state of things are that have been traded there. And it will pull out the latest rows for that group by. So this is effectively a time-based group by. And then, apologies, my clicker stopped working. Okay.
Okay, we'll advance. Oh.
Oh, okay, thank you. Thanks. So in this case, this is another time series join. So in this case, the top, this is looking at fields from one table and then time aligning fields from another table. So it's effectively doing a relational join, but finding the nearest match. So in this case, we're asking in 2016 for these specific taxi rides, what was the weather like? And this, for example, may help you if you're trying to do some analysis of taxi rides that have happened in the past, and you want to understand the best profitability based on weather or something like that. So you may need to join pieces of data that align in sort of this semi-fuzzy way. But the next thing that I want to talk about is that with time series introduced, that's only really a fraction of what most organizations need to do. And it's how all these type of things can be integrated in a more general data stack. And the technologies that we're seeing evolving based on what our customers are asking and effectively the stuff that we're trying to make sure that continues working. So you know what the modern data stack looks like. It's frankly a large number of buzzwords at the end of the day. It's on cloud, it's on-prem, it's confusing, it's different for everybody, and there's no single answer of any of this. But there's a few things that we see coming out more and more, and this is the fact that often people want to be able to write code, not just queries. There's a few interesting technologies coming in the space. And of course, there's the big elephant in the room of the other thing that everybody's trying to integrate and use as a fancy technology. No, not that one, though we're using that one too. It's obviously AI and how that affects everything. So the first is that the first interesting technology is probably Parquet. And if you think of time series as data coming in, if it's coming in at a constant and big enough flow rate, then eventually you're going to run out of local storage. And we've got customers that are writing on a single instance over 1 terabyte of data per day. So that's gonna, you got to put it somewhere after that. So really we partition. So you've got today or weekly, depending on what our customer usage is, you partition. And what we can then do is take one of those partitions and convert those partitions effectively for soft archival, or we call it cold storage. And you can shrink it and compress it as you do that, and then access it as if it were one thing. So within the database itself, you can ask for the latest data. It's all there, but if you go back in time, it'll effectively fetch it from S3 or Azure or whatever your data lake or preferred technology for these things is. And that's effectively Parquet, so it separates out your live data from your older data that you may want to throw some MapReduce style of computation on top to actually make some meaning out of it. And integrate it with other tools as well, be it Python or other query engines on top of that. The other thing that I forgot to mention is that we're also doing the reverse. So if I look back at that example of the data fields that you may want to capture for a taxi ride, these aren't time series, are they? These are really identifiers into other data sources. And so it would be really nice if you can just do a query and sort of grab that data in. And so you can connect an external data source, assuming it's, in this case, a whole directory full of Parquet files. But then, there's other data sources that you can plug in, because, yeah, you need that stuff. And then the other thing that I think is really interesting and useful is the convergence of us and, as far as I can tell, pretty much all of the database vendors out there, looking at integrating data through Arrow. And Arrow is really a set of common constructs, and they're layered. So if you want to share stuff within your own process between libraries, for example, that's an easy way of doing that. But then that gets stacked through inter-process communication and all the way to things like Arrow Flight SQL. And where this comes interesting is if you have queries where your result set is really, really large, then you find that you're no longer dominated by the speed of your query engine, but your ability to transfer data in bulk from one place to the next as cheaply as possible. And for that, there's really two things that we're looking at. One is how to solve that over the network, and that's Arrow Flight SQL for the most part. And the second is how to do that over the same host. So if you want to co-locate your data and your compute as close as possible, then effectively get something like a select star from table to be free. So even though you may have a couple of 100 gigabytes on disk, so long as it figures out where everything is, it doesn't matter. You can just plug in your other tool, and you should just be able to look at your data in, I don't know, like Polars or Duck or whatever it is. And last and finally, we're also extending the type of columnar types that we support. So we're looking at integrating vector types, which are multidimensional. And these are obviously useful for pretty much anything, but anything that you do, whether it's embeddings or machine learning of any sort, but also in the financial space, if you want to even represent something like a volatility surface, then doing that without being able to represent a multidimensional matrix, that's pretty hard. So that's kind of where we're going with this stuff. Hopefully that's helpful. That's us. And yeah, thank you.